In this lecture, I'm going to explain about bipolar transistor configurations. What is configurations? Bipolar transistor connected in a network. Then how this transistor 3-terminal device can be connected in any networks. As we have seen in the p-n junction diode, of these 2-terminal p-n junction diode connected in the network as forward bias or reverse bias connection. When it is plus is given to p type, minus is given to n type, forward bias, and when we connect opposite, we will achieve reverse bias. But whereas in 3-terminal transistor connected in the any network which is connected in series network, it is not possible. So we can connect a 3-terminal device in such a way that one terminal is common. How these 3-terminal can be configured in the network can be discussed now. We will see now. As the bipolar transistor is a 3-terminal device, there are basically 3 possible ways to connect it within the electronic circuit, with one terminal is being common to both input and output terminals. Based on those connection, one terminal is common, we can categorize these configurations can be common base, common emitter, and a common collector. First we will see that common base configuration. What is common base configuration? And what are the connections of common base configuration? And what is the operation when the transistor is connected in common base configuration? This is the simple connection or simple representation of common base configuration. In this configuration, as I said, the base terminal is connected to ground. If one terminal is connected to ground, and the remaining 2 terminals will be connected as input terminal and output terminal. So in this case, it is a common base configuration. In this common base configuration, among 3 terminals, emitter, base, collector, in this base terminal is common, connected to ground, and input is connected to emitter terminal and output is connected to collector terminal. The name itself says that whenever common base means what base terminal is common. So here I am connecting ground and emitter terminal is connected to input and a collector terminal is connected to output. If it is PNP transistor. If it is NPN transistor, the N-type emitter is connected to input terminal and the N-type collector is connected to output terminal, and P-type base is connected to ground, common ground. So irrespective of the type of transistor, the middle base terminal is connected to common. When it is connected to common, it is common practice that in order to explain all configurations, so input terminals, like input of this configuration must be forward bias, so that in order to connect forward bias, plus and minus is given to emitter and base, and collector base junction is reverse bias, so that we can connect minus and plus. So when we connecting this way and see that operation, and then we have studied about how this configuration is helpful in the electronic circuits. The symbol notation for this common base configuration, when we see this symbol, so base is connected to ground and the collector output, emitter is input. When we see this type of diagrams, we have to be noted currents and voltages. The current at each terminals and voltage at input side and output side. The voltage measured between input terminal with respect to ground is called VBE, base to emitter voltage, and the voltage measured between collector and base terminal is called VBC, and the current measured in the emitter terminal is called IE, and the current measured in the collector terminal is called IC, and the current measured in the base terminal is called IB. In the previous lecture, the notation for the current direction according to the Kirchhoff current law. So here emitter current is entering, so that base and collector currents are leaving. In NPN transistor, emitter current is leaving, means remaining base and collector current is entering. So this is a simple block diagram which represents the common base configuration. But in order to understand the behavior of the common base configuration, we have to provide the proper biasing, we have to provide to the proper resistance, and provide to measure the voltage by providing voltmeters, to measure the current by providing ammeters. So let us see that the common base configuration behavior can be explained by two set of characteristics, which are called input characteristics, also called driving point characteristics, and output characteristics, also called collector characteristics. What is input characteristics and what is output characteristics? Before going to a particular configuration of these characteristics, I would like to explain the simple general definition of input characteristics for any configurations we can apply. So what is input characteristics? Generally, the word input means the graph variables also related with the inputs. So input characteristics is the relation between input current versus input voltage. Input current versus input voltage. By keeping output voltage constant. This is the general definition for input characteristics. It is a graph or it is a plot between input current versus input voltage by keeping output voltage constant. That is called input characteristics. Then we can apply this general definition to all configurations: common base, common emitter, common collector. So what is output characteristics? What is general definition for output characteristics? General definition for output characteristic is, it is a graph between output current versus output voltage by keeping input current constant. Input current is constant. So in this, now this general definition of input and output characteristics can be applied for common base configuration. When we apply the common base configuration, same, what is input current? Here it is input current is IE, because if you take the symbol, transistor symbol for common emitter, common base, like base is connected to ground. Emitter input is given to emitter terminal, output measure at a collector terminal. So the current flow in the input terminal is called input current, which is called IE. The current flow which flow in the output terminal and measure their at output side is called output current, which is called IC, and it is current flow in the base terminal IB. And voltage measured between emitter and base terminal is called VBE, and the voltage measured between collector and base is called VBC. So these four parameters: VBE, VBC, IE, IC. Two currents, two voltages. One input current, one output current. One input voltage, one output voltage. These four parameters will be helpful to define the input characteristics and output characteristics for the general definition of these two characteristics. Now, According to the input characteristic general definition, it is the plot between input current and input voltage. What is input current here for the common base? So for the common base terminal is common, emitter is input, so IE is the input current. Here IE is the input current. IE is the input current. When it is input current IE and input voltage between input terminal and with respect to ground terminal, common terminal, VBE, base to emitter voltage. So it is a graph between IE and VBE by keeping output voltage. What is output voltage? VBC. Base voltage between collector to base, VCB or VBC, no problem. So it is a plot between IE VBE by keeping VCB constant. Similarly, this output characteristics, it is a plot between output current. What is output current here in the common base? Commutator, collector is the output terminal. So IC versus output voltage in the common base configuration, VBC. By keeping output voltage, input current is constant. What is input current here? IE. IE is the input current. By keeping input current is constant. Now let us see that by connecting input characteristics, the circuit diagram arranges to reach the input, to measure the input characteristics, and then plot the input characteristics and see the behavior of the device at the input side. This is the common base configuration circuit diagram arrangement to measure the input current and input voltage, output current and output voltage, or simply can say that input characteristics and output characteristics. So let us see that the diagram representation. Take the first symbol of transistor symbol, is a NPN transistor. The type is BC107, one of the transistor type, and draw the first symbol of the transistor. So take the base terminal connected to ground, extend it to this base terminal connected to ground, and this emitter terminal is connected to input terminal and the collector is output terminal. So it is very simple to connect. It is ground and it is input and it is output. But we have a battery. By providing batteries, the battery is called, one battery is called emitter side battery, VEE, and another battery collector side is called VCC. By providing batteries and resistors, proper biasing, polarities of batteries and proper resistor connected to input side, proper voltages and biasing resistor connected to output side to get biasing circuit to be used as this transistor as a operated as like application circuit like amplifier. So by providing this battery input side and output side, and then we want to see the behavior of the characteristics, we must to measure this input current, input voltage, output current, output voltage. How can we measure? By provided with this ammeter and provided with this voltmeter. Okay, we have 2 voltmeters and 2 currents. Students, remember here we always ammeter connected in series in the network and voltmeter always connected in parallel inside the network. So we always measure a in parallel voltage. We always measure a current in series. That's why the ammeter measure in series, connected in series, and voltmeter connected in across 2 terminals. So we have used 4 variables like 4 parameters: input current, input voltage, output current, output voltage. Input current measured with this ammeter, input voltage measured with this voltmeter, output current is measured with this ammeter, output voltage measured with this voltmeter. So now here, what is the range of this for voltmeter and ammeter? When we see this input, it is an emitter terminal. Emitter always emits large number of charge carriers and always measured emitter current in milliampere. So we have to use that in the ammeter is milliammeter. The range for milliammeter is 0 to 200 or 0 to 100. We can use here is 0 to 200 milliampere. And voltmeter, to measure the voltage between emitter terminal and base terminal, we got to use this voltmeter, which the range is 0 to 20 volts. Similarly, voltmeter between collector to base, we can take this voltmeter 0 to 20 volts range. And collector current is also measured in milliampere, so we can use 0 to 200 milliammeter. So this is the arrangement. Very simple. Take the transistor, connected as a base is as a ground, common base. Provide the battery, provide the resistor at input side and output side. So we need to measure the current, put the ammeter. We need to measure the voltage, put the voltmeter on both sides. That is enough. So this is simple arrangement for circuit diagram, common base configuration. Now, by following some procedure to measure input characteristics and output characteristics. First, we will see that how to measure the input characteristics. This is the simple procedure for finding input characteristic curve. The simple step, by seeing this diagram, very simple. In order to measure the input characteristics, the first step is adjust collector voltage to some positive voltage. What is collector voltage? It is a output voltage. So here, the procedure for input characteristics, first step is adjust collector voltage to some positive voltage. What is collector voltage? Nothing but output voltage. Keep output voltage constant. The first step is keep output voltage constant. Keep collector base junction constant. How can we keep collector base junction constant? By keeping a constant voltage at a collector VCC supply. So by putting constant voltage at a VCC supply and then varying the input voltage, input battery, emitter voltage, varying the emitter voltage, and measure the current flow in the input terminal through the ammeter and voltage across between emitter and base terminal measured using voltmeter. That is called input characteristic steps. Take the output voltage, nothing but collector voltage constant, and then increasing the emitter voltage, input voltage, increasing the input voltage or input battery, and measure the input voltage and input current in a small suitable steps and record the corresponding values of the emitter current each step, and then plot the graph between input current versus input voltage VBE by keeping output voltage constant. That is, we can observe here. So fixing of this output battery so that we can fix the collector base junction voltage, and varying the input voltage, note down the input current IE and input voltage VEB. So here, by taking some example, let us say 1 volts. I am keeping output voltage like 1 volt. By keeping output voltage, keep 1 volt, nothing but reverse bias voltage between collector and base is 1 volts. And then varying the input battery and note down the input current and input voltage in a suitable steps, and take all the points and join all the points and plot the graph. What is the resultant graph? We'll see here. This is the graph. By keeping input voltage output voltage VCB is equal to 1 volts. This 1 volts, keep 1 volts output voltage is equal to 1 volts. And by changing the input battery, note down the input voltage. Okay, by increasing the input voltage like 0.0, 0.1, 0.2, 0.3, 0.4 likewise. When we increase in suitable step, then we will see the graph will like this. You will get the graph, first graph. What is the similarity of this graph with the PN junction diode? If this diagram, if it is a NPN transistor, NPN, this output side keep fixed at 1 volt, then varying the input voltage, this is plus is connected to P type, minus is connected to N type, which is nothing but simple forward bias connection at input side. When input is forward bias connection, then varying the voltage, note down the current, it will look like it is similitude of the VA characteristics of the PN junction diode. So input junction is forward bias. So the up to some cut-in voltage, which is called 0.6 for silicon, 0.3 for germanium. Before cut-in voltage, it shows no current flow. Once it reached cut-in voltage, the minimum voltage to establish the current in the emitter base junction. Then the current flow in the emitter through base is exponentially increasing. So this kind of graph will achieve from the procedure. In the second step in this procedure, we followed, keep some other voltage, like we increasing the output collector to base voltage from 1 volt to 10 volts. By changing the output voltage collector to base voltage from 1 volt to 10 volt and keep constant, and come to input side, again input side, follow the same procedure, varying the input voltage, note down the input current and input voltage between emitter and base. When we see the second case, so again up to some cut-in voltage, and then after reaching the cut-in voltage, the curve moves exponentially. Similarly, in the third case, curve moves exponentially after cut-in voltage. What should be the observation here? By seeing this graph, input characteristics, we have to observe that by increasing the collector to base voltage 1 to 10 to 20, the curve moves left side. From this curve to this curve. The curve moves left side, that is first point. And when we increasing the output voltage collector to base voltage, the maximum point, the maximum current, corresponding current, emitter current, is increasing. It possesses the increased current at the input side by changing the output voltage from 1 to 10 and then 20. When we recollect this concept of operation of the bipolar junction transistor, we can get through why this happened. What is this breakthrough of current increasing by changing the collector to base voltage from 1 to 10 and then 20. First, we will see that why this current emitter current increases. What is the reason that emitter current increases? As we have seen that it is a 3-terminal PN junction diode. Okay. So if it is NPN or PNP, input is forward bias, output is reverse bias. When it is reverse bias, okay. So when the reverse bias between base and collector, junction width increases. This junction width increases. When compared with the emitter base junction, collector base junction is more. When depletion width or junction width increases by increasing collector to base voltage, base width reduced. In the second case, in the third case, by I am increasing further, that base, the depletion width, depletion region inside the base region increases. When base width, depletion region increases, base width further reduce. Now see, when as we increasing the collector to base voltage from 1 volt to 10 volt, then base this depletion region increases. When depletion region increases, whatever the charge carriers of electrons, majority charge carriers of electrons move from N to P region, emitter to base and reach to collector. Okay, when base region reduced, then the recombination in the base decrease. When the recombination in the base decrease, the number of charge carriers recombination takes place in the base region decrease because of a small thin region in the base. Already it is a thin region. Again, due to depletion region, due to collector base junction increases, base width decreases, then base current decreases. When base current decreases, automatically collector current increases and emitter current increases in result. So here IE current comes. So 100% current comes from 100% current comes from emitter. When reverse voltage increasing from 1 volt to 10 volt, the depletion width increases. Depletion width increases. The depletion width this much increase. When depletion width increase, automatically this base width decrease. When base width decrease, the current flow in the base is only 5% or 10%. When only 10% recombination takes place and 10% current flow in the base region, then remaining 90% reach to collector. So in this case, when again I am increasing 10 volts to 20 volts, so further this base region decreased by increasing the depletion width. The collector base depletion width increases. Only small base region. This small base region, again this current flow in the base is reduced. Then what happened? The current emitter current which reached to collector current is 90 to 95%. So the emitter current reached to collector increase, so that by increasing the reverse bias connection at output side VCB from 1 to 10, it will be emitter current increases. Further increasing reverse voltage, further increasing IE current. That is the reason. And second reason why the curve move towards the y-axis. Y curve from first curve to the left, next curve, it moves left side towards to the y-axis. What is the reason? Will same thing happen here. Same thing happen when reverse voltage increases. So here, if you take the graph, I am taking it in order to clear explain. I am taking this graph like this. This is the first graph, this one. This is the second graph. This is the third graph. If I am taking this way. Now, this is the base to emitter voltage. I am taking a constant line here. I am taking a constant line. These are the cross section point. These are the cross section point. If I am taking, I am clearly draw this one. this one, this one, this one. If I am taking constant line, now when VCB is equal to 1 volts and increasing the emitter to base voltage, so it reaches, for example, 0.6. At 0.6 it reaches this current, 1 milliampere current. When increasing the collector to base voltage, to 10 volts, so now I am increasing the base to emitter input voltage from 0.1, 0.2, 0.3 and so on. So now in this case, by increasing the collector to base voltage, base depletion width increases, base width decreases. When base width decreases, so the region, the PN junction forward bias region, this forward bias between this small region of base and the large region of emitter. So that when the base region reduced, so it requires less voltage to get the same current. For example, this line, if you take the 2 milliampere current, so in order to get the 2 milliampere current for VCB 1 volts, it requires 0.6 volts. When reverse voltage increases, base width decreases. So in the next time, by increasing the input voltage VBE, it no need to reach to 0.6. Earlier than 0.6, 0.58 only, you will get the same 2 milliampere current. By increasing further 20 volts, again base width reduced like this. The base width reduced. This is a emitter, this is base. So it requires to cross the junction to current flow, start current flow. So it requires 0.515 only. This to get the same 2 milliampere current. So that's why, so here by increasing the reverse voltage, collector base voltage, the input base to emitter voltage require the earlier voltage to reach the same current. That's why the curve moves left side. So this is the two reasons why the curve moves left side and why this curve increasing compared with the 1 volt, 10 volts and then 20 volts. So as we increasing the volts VCB, that emitter current increases. And what are the outcome point from this input characteristics? The most important outcome point from this input characteristic is when the transistor gets on, by keeping output voltage constant, by varying the input voltage in suitable step from 0.1, 0.2, 0.3 and 0.4, 0.6 like that. At a certain point, current start in the transistor. That is called cut-in voltage, or that is called VB cut-in voltage. So that point will clearly says that in order to get on the transistor input side, the input base to emitter voltage must be greater than cut-in voltage, which is called 0.7 or 0.6 for silicon and 0.3 for germanium. So when we reach cut-in voltage, then only when we provide the minimum voltage, cut-in voltage between base to emitter voltage, then only the transistor gets on. When input junction must be on, and in order to get that input must be on, we have to provide the base to emitter voltages minimum 0.7 volts. And that is the one important point. In order to get transistor act as an amplifier, input junction must be forward bias. When it is must be forward bias, you are always graph greater than this point, cut-in voltage, greater than this VBE 0.7 volt. Then only transistor current flow in the transistor and transistor gets on. So VBE on, which is equal to minimum 0.7 greater than or equal to 0.7. And the second outcome from this input characteristic is measure the input resistance from the graph. It is a plot between input current, input voltage. So by measuring the point like a DC resistance or AC resistance, if you measure the DC resistance, take one graph and put a point, and corresponding voltage and corresponding current. Ratio of that R input resistance is equal to is a DC resistance or static resistance VBE divided by IE. If you want to measure the dynamic resistance, take this one graph and change in voltage and that is the corresponding change in current. When we measure a change in VBE and change in IB, take delta or change in voltage VBE and change in current IB, we measure by keeping output voltage VCB constant like 20 volts graph. Change in voltage by change in current is called dynamic resistance. This resistance is very low in the emitter base junction because it is forward bias. So a less resistance, less input resistance have observed in the common base configuration. Next, we will see that base width modulation. What is base width modulation? So base width modulation, according to the procedure, increasing the collector voltage and keep on increasing collector voltage 1, 10, 20 and observe input current and input voltage. What happens when we still increasing to a certain limits? When we increasing the collector to base voltage, if you see this diagram, if you see this diagram, this is reverse bias junction, this is forward bias junction. By increasing the reverse voltage, junction width increases, base width decreases. I am still increasing 10 volts, 20 volts, 30 volts, still increasing. Base width, junction width increase, base width reduce. I am still increasing. Junction width increase, base width, base region decrease. This process of increasing collector base voltage increases, resulting in junction collector to base emitter junction, collector to base junction increase, so that base width decrease. This process of base width decrease is called base width modulation. The change in the base width is represented by base width modulation, or also called early effect. The emitter by base diode characteristic shifts upward by increasing the value of VBE, VBC. So this occurs due to phenomenon called base width modulation. So why the graph moved this way and why the graph moved towards to the left side is the only reason is base width reduce or base width modulation or early effect. So what happened? What are the consequences when we goes on increasing the base width, goes on decreasing the base width by changing the reverse voltage? So there are two important consequences happen in the common base configuration by following the early effect. So here, a recombination in the base decreases by changing the reverse voltage. Base width decreases, only less recombination takes place in the base region. When less recombination takes place in the base region, so that the current flow in the base is reduced. Current flow in the base region is reduced. When the recombination less in the base region, so the remaining current reach to collector. But what happens when we goes on increasing the this early effect? So when increasing the early effect, so alpha increases with VBC increases. Alpha increases. So alpha is nothing but it is a current gain in the common base configuration. Current gain nothing but output current by input current. Output current IC, input current IB. IE. So it is a ratio of IC by IE. It is a ratio of IC by IE. So when base current is decreases, recombination decreases in the base current decreases, so automatically the collector current reached collector increases, so alpha increases. When we goes on increasing this reverse voltage, at one certain point the base width gets reduced to 0. So base width reached to 0 width, and there will be no base, the base region is disappear. Then what happened? The direct connection between emitter and collector. Whatever the emitter directly contact to the collector, so that it is just like a contact of two material. So direct current flow from emitter to collector without amplification or without some recombination in the base region, so that it will leads to a large current flow between emitter and the collector region. Then it will goes to a breakdown region. So in order to protect the transistor operated in the breakdown region, we have to must provided with the base region not gets to 0, not get to 0. So which is called punch through. Never operated transistor in the punch through region. Never operated the transistor gets that base region gets 0 by changing the collector to base voltage. We are careful about that limiting of the collector to base voltage, which leads to reduction in the base region. That is about input characteristic. Now output, we'll see output characteristics. To obtain the output characteristics, same the circuit arrangement. Very simple, biasing input and input resistor, output battery, output resistor. If we want to measure the voltmeter, voltmeter and ammeters are connected. If we want to measure output side, we connected output voltmeter and current ammeters. Now, what is the procedure to achieve the output characteristics? We know the definition of output characteristics. It is a plot between output current and output voltage by keeping input current is constant. So in order to get output current and output voltage by putting input current is constant, first we will see that how to put that input current IE is constant. See, very simple, by keep constant of input battery and set at 2 milliampere by varying the input, by varying this input battery, by varying this input VE supply, and keep that input current at 2 milliampere and then fix it and come to output side, and come to output side varying the battery, note down the voltage and note down the output current. That is what happened in the output characteristics. So keep out input current constant 2 milliampere by adjusting this base to collector voltage. By adjusting the VBE, keep 2 milliampere constant and increasing the collector to base voltage in a suitable step and measure the IC, so that we can take the graph between output current and output voltage. See one graph here. This is keep input voltage constant and note down varying the collector to base voltage and note down the current graph like this. Note down the collector current. You will get this graph. And in the next step, repeat the above step for IE with a different milliamperes, like 4 milliampere, 6 milliampere, by changing this output characteristics, by changing this input current 2 milli, and again start from 0 to collector to base voltage, start from 0, 0.1, 0.2, 0.3, and 1, 2, 3, 4, 5, 6, 7, like this. Then you will get the graph like, you will get the graph for 2 milliampere. Okay. So this is the procedure how to get output characteristics. Keep input current constant 2 milli and adjust by adjusting input voltage, and now measure the output voltage VBC and IC by varying the output battery, and note down these VBC and IC values in suitable steps and plot the graph between these two. And again this process repeat for 4 milli, 6 milli, likewise in a suitable step, and see this the resultant graph like this. If you observe this here, this output characteristics having the characteristic graph for this output characteristic of the CB configuration. This characteristic curve can be explained with the three reasons, which are called cutoff region, active region, saturation region. First we will see cutoff region. What is cutoff region in the output characteristics? Suppose I am keeping input current constant at 0 milliampere, which means emitter base junction is 0 volts or emitter terminal is open terminal. When emitter terminal is open terminal, that means emitter base junction is 0, no forward bias. Only focus on output collector base junction. Output collector base junction is reverse bias always in this case. So when we changing the reverse voltage, only current flow between base terminal and collector terminal, the current flow is due to only reverse bias. So which is very low. Reverse bias current always measured in microampere. So when we take the graph in x-axis, y-axis in milliampere, the measured microampere is always negligible. That's why by keeping input current IE 0, by varying the output voltage, even though varying output voltage, but current is 0, which shows the microampere current. Now I am changing the input current 1 milliampere and varying the output voltage start from 0, and then you will get this graph. And this graph, so in this case, IE 0 means input 0 means no forward bias. It is also reverse bias. So whenever it is 0 means input junction is reverse bias. So input junction reverse bias, and by varying the collector to base voltage means reverse bias increasing. So this is reverse bias. Both the emitter base junction and collector base junction is reverse bias, which is in cutoff region or cutoff mode. Transistor operated in cutoff region. So both junctions are reverse bias. Suppose I am increasing the emitter current to 0 to 1 milli. How can we get 1 milli? Definitely that emitter base junction must be forward bias. Must be greater than cut voltage. So it is forward bias. Now changing the input voltage, note down the current. By changing the input voltage greater than some VC set, then entire region is called reverse bias. So this region, above this region, emitter, due to emitter greater than 0, emitter current, forward bias. This collector to base voltage greater than saturation point, for example, this is the saturation point. So all entire region is reverse bias. So forward bias and reverse bias in the blue color region, all blue color region is called active region. What about saturation region? In this saturation region, I am keeping IE greater than 1, nothing but forward bias, all these reasons. And in this common base configuration, we must focus on this minus 0.1 to 0. In this minus 0.1 to 0, when we keep input current constant to 2 milli, immediately in laboratory when we see this, collector to base voltage which shows some 0.1 or 0.8 or 0.9. Initial value is 0.9. That minus 0.9, it shows minus 0.9. Now varying the collector to base voltage, when we changing the output side, this minus 0.9 to this 0, in this region, a sharp increment, a small change in voltage, minus 0.1 to minus 0.8, a sudden increment in the current, large change in the current. A 0.9 to 0.5 immediately reach to maximum point. So when collector to base voltage reach to 0, it reach to IC max. So then after greater than 0, when irrespective of values 0, 1, 2, 3, 4, 5, 6, 10, 5, 10, 15, that the change in the current is constant. It's almost constant. That is the characteristic behavior of the transistor in output characteristics. Within a sharp time, within a sharp volt, like minus 0.9 to 0, a sharp increment in the region, and then it will maintain the same current by changing the collector to base voltage. Irrespective of collector to base voltage, it is constant. So this region is called saturation. So if you take some other voltage, 6 volt, 6 milli, it shows minus 0.1. So again, changing this minus 0.1 to 0, immediately increasing the 6 milliampere, and then it will maintain constant. So this region is called saturation region. In this region, IE greater than 0 forward bias, VCB minus 1 to 0 forward bias, both forward bias, it is called saturation region. Now, what are the outcomes from this output characteristics? We can measure output resistance. What is output resistance? Take one graph, change in voltage. This is change in voltage, change corresponding small change in current. You will get R is equal to large change in voltage, small change in current. Small nothing but denominator, you will get large resistance. So in the common base configuration, you will get input resistance is less, output resistance is very large. Okay. So, and also one more important thing is, in the output characteristics we can get that what is the gain. The gain in the common base configuration is called alpha, and I will explain what is the alpha and what is the definition of alpha. So gain is gain in the output characteristics, output current by input current. What is output current here? IC. And what is output current IC? What is input current IE? So when we see this any point, so almost if you take this one, almost same current. If it is for corresponding volt, if you take the constant voltage, a point, what is the emitter current? 4 milliampere. What is corresponding collector current? Almost 3.9 or 3.98. You will get approximately equal to 1. That means unity current gain for common base configuration, which provides unity current gain. So these are the points we have observed in this common base configuration. This is a clear picture in the saturation region, how they are increasing linearly with a sharp voltage increasing in the saturation region. And then this configuration, we can measure the collector current IC. So in this configuration, what is the total collector current? If it is, this is the common base configuration, input junction must be forward bias, output junction must be reverse bias. So due to forward bias, large current flow from emitter to collector. Due to reverse bias, small current flow. But reaching current, total reaching current is small minority current and majority current. IC majority and IC minority. This can be measured by open circuit input. Only measure the output current reached to collector by measuring the reverse bias, which is called minority current represented by small arrow, IC minority, which is called IC B0. When we neglecting this output side, open circuit, and measure the input to majority current, you will get forward bias current which reached to collector, which is called alpha IE. Alpha times of IE. So collector current IC is equal to majority current is IE alpha and minority current IC B0. What is IC B0 means? Collector to base voltage when emitter terminal is open. Emitter terminal is open, nothing but input forward bias is 0. So that this type of minority current represented by small arrow and alpha IE times nothing but majority current from emitter to collector. So this one, for example, I am 100% reach to collector. Which type of current? So alpha IE times and alpha IC B0 time, IC B0 current. So that majority and minority current. When we neglecting this one, you will get IC is equal to alpha IE. This relation is used in common base configuration. Alpha is equal to is the gain, output current IC by IA by neglecting this term. So alpha is equal to IC by IA. This is the correct current in the collector current, most important formula by measuring the current flow, collector current in the common base configuration. They have given this type of problem. What is they have given common base current gain alpha and emitter current in some milliampere, and reverse saturation current or collector to base current when emitter is open is some microampere. Then what is the collector current is to collector. Okay, so that we can measure the collector current. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.